but we say that T0 is also a Toeplitz matrix as defined above. Similarly, T-1 is a matrix that repeats along all the block upper triangular entries. That's also Toeplitz. T1 along the block subdiagonals, that's also Toeplitz, and so on. Okay, so the matrices that we're dealing with are of course dense, but we can still generalize this definition to level K Toeplitz matrices to deal with problems in higher dimensions. Similarly, we can generalize the notion of a circular matrix. A circular matrix is a Toeplitz matrix, but it has the additional property that its columns consist of cyclic permutations of its first column vector. What this means is that if you have an entry C1 on the lower triangular, for example, C1 also has to appear on the top right. Okay, so the entries rotate, if you like, so that you have this additional structure. You can define level K circular matrices as in the Toeplitz case. So for example, a level 2 circular matrix would be a block circular, but all the matrices involved are also themselves circular. A key property of circular matrices, a very special class of matrices, is that they may be diagonalized by the Fourier matrix. Fourier matrix, of course, can be applied very cheaply on a computer using the fast Fourier transform. And the circular matrix can be diagonalized by this. Fn is the discrete Fourier transform of size n. Lambda is a diagonal matrix containing the eigenvalues of C. That's also very convenient because it can in fact be obtained by applying a Fourier transform to the first column of C. Okay, so level K circular matrices possess an analogous Fourier diagonalization property, which I'll describe. And what this means is that any level K circular matrix can be multiplied by a vector in big O of n log n operations, where n corresponds to the dimension of the system. So it's a really convenient problem of circular matrices, one that we're going to take advantage of. So now I introduce the problem that I want to apply this to. So we have this quite familiar differential equation structure here. It consists of a mix of Caputo derivatives in time and Riemann-Liouville derivatives in space. This is applied to our state variable y, but we also apply our control variable to a PDE as well as a fixed given function. And we write this in optimization form, such that we also have box constraints on y and u. So this is posed on a space-time domain. Alpha, the order of differentiation for the time derivative is between 0 and 1, and beta 1 is between 1 and 2. So to allow this multi-level Toeplitz structure to hold, we assume that omega, the domain, the spatial domain, is a rectangle, but this can be generalized to a cuboid in 3D or a d-dimensional orthotope in higher dimensions. So this is the requirement that leads to multi-level Toeplitz matrices. They have many applications, and we equip it with an initial and Dirichlet boundary condition. The way that we solve this problem is we use what's called a discretized and optimized approach, which involves building a discrete Lagrangian based on the problem formulation that I've shown you. So we discretize the problem here. So A is the matrix that discretizes the fractional differential equation. M1 and M2 are terms that approximate the integrals in the cost functional. Okay, so after building the Lagrangian, we then obtain optimality systems. This just gives precise details about what A is. It's the term arising from the Caputo derivative, Kronecker product with an identity matrix corresponding to the spatial dimension, minus an identity corresponding to the number of time points, Kronecker product with the discretization of the PDE, which involve these symmetric dense matrices coming from the Riesz term. Okay, so a technical thing that we do before we start is that we multiply this constraint by a constant to ensure that the sequence produced by the generating function of the resulting matrix is absolutely summable. So a theoretical requirement, so we just multiply the PDE constraint to obtain this completely equivalent constraint. Okay, so what we get when we come up with the optimality conditions for this problem in terms of YU and the Lagrange multiplier P, we get this system here. This is a standard saddle point system obtained by taking optimality conditions from an optimization problem. So we can solve this using MinRes, the standard iterative method for symmetric indefinite problems, which is what this is. Okay, in certain cases, for example, diagonal M1 and M2, which we indeed have for this problem, they're positive definite diagonal matrices because they're a finite different approximation of from the integral terms. We can reduce the system to this nice form here. So we can reduce it to a Schur complement matrix and instead tackle this system. So I'll explain how we can precondition either of these systems. So just a reminder, we're solving this on a rectangle in space, and there's also a time dimension. So for a 2D problem, we're going to be looking at level 3 Toeplitz matrices as I've defined above. Okay, so just to give a little break, a little perspective here. So for these optimization problems, if these were PDE constraints, the matrices here, in particular the matrix B, would be sparse. So within a linear algebra solver, there's some structure we'd be able to exploit there with sparse linear algebra. But with FDE constraints, this isn't the case. B will be composed of dense matrices. However, there is a lot of structure here arising from the multi-level Toeplitz matrices. So this is something that we can and do exploit. The way that we do this is through multi-level circular preconditioning, which I will just describe, but there are other approaches for making use of this structure. So one other that I've been involved in is to regard this as a high-dimensional tensor equation and build low-rank Krylov methods. And this, in some sense, exploits some of the structure that we have from these, in effect, highly structured matrices. So although someone coming from a PDE background like myself doesn't have the sparsity of a matrix that I would have if these were more standard PDE like the heat equations, there is some structure there which people in linear algebra can take advantage of with an iterative solver. And I'll point to a talk by Marty tomorrow who I think discuss some of these ideas in the context of low-rank solvers. Okay, so the idea of multi-level circular preconditioning is what I want to talk about now. So these arise, multi-level Toeplitz systems arise in a range of applications. Direct solvers can be valuable but can also be unstable. So, and of course, as I mentioned, we don't want to store the entire matrix that arises. Iterative methods with circular preconditioning provide a valuable alternative. In particular, Chan came up with this very nice circular approximation to a general Toeplitz matrix where you minimize the distance between the circle and the Toeplitz matrix. In the Frobenius norm, this has an expression which can be clearly written out in a direct way. And Chan showed that the precondition matrix here has eigenvalues clustered around 1, which is what we want. We like clustered eigenvalues. Okay, furthermore, if you have a symmetric positive definite Toeplitz matrix, then we have a circular approximation with the same property. This can be generalized to higher dimensions, okay, using a recursive linear algebra. So for example, if you had a level 2 Toeplitz matrix rather than simply a Toeplitz matrix, what you can do here is you can take a circular approximation to each block. You take a circular approximation to each Toeplitz matrix which arises. Then each each of these blocks here can be diagonalized by a Fourier matrix. So you can apply a Fourier matrix, okay, a Fourier transform, effectively to this system, Fn inverse on the left, Fn on the right, so that you permute this matrix to be such that all the matrices here are diagonal. You can then apply a further permutation such that you permute the system to a block diagonal matrix where all of these matrices are themselves turtlets. That's a very nice linear algebra feature here. But then when you have turtlets matrices on the diagonal, you can then apply Fourier transforms again to diagonalize these matrices. So using just FFTs, permutations, and an eigen decomposition at each level, you can generalize this circular approximation to higher dimensions, and this can be completely generalized to level k turtlets matrices on the domains that I described using a recursive linear algebra. Computational complexity again, n log n, and very low storage. Okay, so how do we apply this to our system? Well, this is the system that I said we had if we take the Schur complement term and build the symmetric positive definite system that we can apply within conjugate gradients. We can then take circular approximations to each block. So this is a level 3 circular approximation to D. Okay, exactly as described on the previous slide. You can take a level 1 circular approximation to M2 because it's diagonal and this form here and repeating. And the nice thing about the decomposition is that the fact that you have these Fourier transforms is that the Fourier matrices cancel out when you multiply terms together. So this is a very nice and efficient approximation to apply its inverse to a vector. Similarly, you can design a solver for the saddle point system itself, where you have terms for one block and then analogous approximations for the Schur complement. One thing I just want to describe briefly now is that you can add, so far I've discussed solvers without additional box constraints. What we want to do is we want to generalize these solvers for problems with box constraints on y and u. What optimization method should we use to treat them? Well, a lot of the standard approaches either destroy the turtlet structure or they select a subset of the entities which has the same effect. So what we do is we employ an alternating direction method of multipliers, a first order method of ones you have very good experience with in terms of convergence, leading us to achieve about 4 digits of accuracy while preserving the turtlet's structure, which is very nice for us. You can see the only change in the resulting linear system is that at each step of the ADMM, you add these nice identity matrices to each diagonal block here, and you subtract it here. So this system is actually nicer in many ways than the system I've shown you without box constraints. But the thing is, we do have to apply ADMM a number of times, so that's where the additional cost comes in for that more difficult problem. So I just wrap up by showing some numerical results. We take a square as a test domain and a reasonably challenging desired state. You can see some plots of what we're trying to drive our solution to below. Experiment 1 doesn't consider additional bound constraints. It fixes the order of differentiation and the regularization parameter gamma, okay, and varies the size of the matrix system. So you can see as you increase the size of the matrix system, number of iterations doesn't stay constant, but it doesn't increase too badly either. And note that this system here is about a size of 40 million by 40 million dense system. So being able to use this recursive linear algebra and solve such a massive dense system in an hour or two is something we were very happy with. And this can be generalized to MinRes as well, but that takes more iterations and we know why from a theoretical point of view. Experiment 2 varies gamma, and what we see here is that constraints with the ADMM approach and see how the behavior varies there. Again, we're seeing some nice behavior in terms of problem size. The number of CG iterations actually stays pretty constant. The number of ADMM iterations this time increases generally as the problem size increases, but we can still solve these really big and quite difficult problems in a modest CPU time. We can also apply this if you only apply box constraints in one variable only. You can vary the fractional order of differentiation. This is perhaps worth noting. All of these problems we can solve efficiently. The toughest problem, as you might expect, is with alpha being relatively large and beta being relatively small. So I think this has been closer to an affection type problem as opposed to a heat equation type structure. Okay, and finally, experiment 5 introduces these box constraints, but now varies the regularization parameter, and reassuringly we see the same thing, which is that if gamma becomes small, then the Schur complement becomes much easier to approximate, so the CG iterations decrease. So overall, we can solve a number of these problems in quite low CPU times by exploiting this really nice circuit, a multi-level circuit and structure. You can then apply using graphics FFTs. So we've constructed a matrix-free method to solve a number of optimization problems, and my focus in this project was considering fractional differential equations. So thank you for inviting me to speak here. We can apply ADMM with this preconditioner to solve space-time problems with inequality constraints. This is a very challenging problem in this area. The memory requirements and the complexity was low and can be generalized to higher order FDs. What I didn't talk about is that we also devised some GLP theory to justify our preconditioner, which I know a lot of people in the audience will be very familiar with. So these have some really nice applications, so I'd be very happy to speak with anyone who's looking at problems that could be modeled using this optimization framework. And thank you very much for your attention. Matrix which you could approximate in circular form. What I'm not so confident on is whether the control would have the control variable would have sufficient regularity to allow us to apply the differential term within the cost functional. So that's more a PDE analysis point of view. So I'm not quite sure whether you could apply a general fractional derivative within that term for reasons of regularity. I'd have to think a little bit about that. But if we could, then I think the method could be generalized in this case. The difference here would be in this matrix here. It would probably generalize to a block matrix where the blocks have a more complicated structure. So yes, that could be fine.
in Texas at Texas A&M University. Among other topics, he works on inverse problems, regularization, partial differential equations from many perspectives, modeling, numerical methods, and of course, on fractional differential equations. Today, he will show us how to discover fractional diffusion models from observation, at one point. Please, Professor Jean.
Can you hear me?
Yeah.
Okay, thank you. Yeah, thank you very much for the really nice introduction, and also thank you for the invitation to give this talk. It's really a great pleasure. So today I will talk about fractional diffusion models, try to infer models from one point observation. And this talk is based joint work with Yava Qian and Zizhou. So my talk will be divided into 3 parts. So the first part, so I will briefly recap the model and also the motivation. And then I will discuss 2 problems in some detail. One is how to determine the order in the model, so from the given data. And another one is a bit more challenging, so we try to determine the coefficient and other parameters. And throughout the talk, so I will show you some numerical results and also ideas, the main ideas. And hopefully, so I can convince you that actually, so one can do something with the fractional diffusion model just with very simple given data. So actually, I do not need to show the slides because everyone here actually knows that it's now widely accepted that time fractional diffusion models, so actually they are very useful for a nominal diffusion process. And these applications, there are actually quite many. So I just give 4 of them. And for example, the earliest one, like Shell and Montreux, so this is one of the earliest ones about electron transport in copier. So they found that this kind of transport process can be decided by continuous time random walk, and later it's equivalent to the time fractional diffusion model. And by now, so there are actually many such models. So one of the model problems we have seen many times in this workshop is the following model problem. So we have this standard time fractional diffusion model, and we have the capital derivatives, which you already see in the previous talk. And in my talk, so I always consider the problem in a bounded domain. And so we have the source and initial condition and some diffusion coefficients or potential term. And I will always assume they are suitable smooth. So I will specify them later, but for the moment, so let's just assume. And the common settings we have seen so far is that in this model, so we assume everything is known except the U. So U is unknown, everything else U is known. So this is a common setting. So we have seen this in many talks. And this kind of problem, so I will call the direct problem. And thanks to the greater efforts of many mathematicians, and including many in the audience. So we actually know a lot about this model given here. So for example, we know that the model is actually well posed in simple function space. And also we have the corresponding regularity theory. And we have seen a lot of numerical studies, for example, efficient algorithm or efficient scheme and convergence analysis or LS estimate. So many things, so actually all of them, so we know quite a lot. And if you are interested in the first 2 aspects, so of this model, so I would like to advertise my textbook here, so which will appear later this month and at spring in this applied mathematical science series. And it contains an overview about this kind of solution theory for the model shown here. So the question I'm interested in this talk is that, for example, in practice, so we are just given some set of experiment data. So this data can take many different forms, and but we do not know the physics process very well. So actually, so how shall we find the proper mathematical model of the anomalous diffusion type to describe this process? So roughly speaking, so there are two different strategies one can follow in order to answer this question. One is that we start from the macroscopic distribution. For example, we start from continuous time random walk, and in this random walk, so there are some parameters we can specify, and then we consider diffusion limit, and this will end up some time fractional diffusion model. And so there's some one-to-one correspondence between these microscopic parameter and the models in the time fractional diffusion model. So for example, the order or other parameters, so they can specify in this way. But however, so this approach will require that we actually understand the physical process relatively well. So in this talk, so I will focus on second approach. So we just assume that we have measured some data, which is corresponding partial information about the solution. And we do a very simple data fitting and try to convince ourselves that actually we can figure out some of these parameters shown in this model. So that's and the specific focus is that we have the observation at a single point on the boundary. So that's the focus of this talk. And I will discuss two cases separately. One is that we try to find the order alpha in this model. And in the second case, which is a bit more ambitious, so we want to identify the coefficient alpha and other parameters. And again, so from one single point observation. Let me just emphasize that this kind of mathematical problem actually has quite a long history. So it was first started by Jin Chun and Masahiro Yamamoto, so in 2009. And after that, so there are many works so in this direction. And I also have been working on this on and off for a while. And if you are interested, so there are 3 review papers listed here. So you can find many details and further reference so on this kind of problem. Let me now turn to the first task. So we try to figure out the order of this fractional derivative. So we consider a fairly general class of time fractional model of this type. So we have this rho, so which is the density and some elliptical operator and the source time. And then we have the Dirichlet boundary condition on the external part of the boundary. And then we also have the initial condition. And everything in red, so I assume for the moment, so they are not known. So this means that we have all these parameters. So these are functions rho, A, and F, and G, U0. So all of them, they are unknown. And for the domain, actually, we also assume that it's not fully known. So we assume that this domain actually has 2 parts. So we have the bigger domain, tilde omega. And then inside, so there's some obstacle, which we do not know. And for this A, so even though we do not know what is this elliptical operator, so we assume that this should be the usual second order elliptical operator. So it's symmetric and coercive. So it has all the nice properties, but we do not know these coefficients like Aij or Q. And for the density again, so we assume that it's bounded from below and above, and it has certain regularity. So that's the setting. And so given this setting, so clearly, so everything is unknown. So everything in this equation is unknown. And what we really know, or we assume we know, is that we can measure the solution U at one point. So this flux, so at this partial mu, so denotes the outward normal derivative at one point x0 at the external boundary. And this measurement is available so for a time interval t minus delta to t. Delta is just small number greater than 0. And so we have this piece of information, and we try to find some information about this very general model. But in the model itself, so we have the form, but everything else is still unknown up to now. And the question is that given this data, so can we actually say something about the model? Find some information about the model. So at first sight, so this seems completely hopeless because we have so many unknowns, and the data given it seems very limited. So there seems no chance that we will be able to obtain anything or see anything about this mathematical model given here. And in order to describe the results, so I need to assume a little bit. So I assume that this alpha so is between 0 and 2. So it can represent either the subdiffusion or diffusion wave equation. And so this is domain, and so has a suitable regularity and all the coefficients. So even though they are unknown, so they also have some regularity. So they are not known. So this is red stuff. So they are not known, but they have some regularity. And also for this source and the boundary condition, I assume that actually it vanishes before the final time. So at some up to some point T1, so which is smaller than capital T, so where we will conduct the measurement. And so before that, actually, so, it will start to vanish. So these are the conditions I will need. And then surprisingly, so just based on these very minimal assumptions, so one can show that actually, given this one piece of measurement on this small time interval, and we can find this fractional order alpha. So basically, it says that one single piece of measurement so can uniquely determine this the type of diffusion process. So we still don't know all the other rho A and F or these other parameters, but at least so what we will know that what is the alpha value. So we have some ideas. What's the type of diffusion process or transport process we actually investigating. And the surprising thing is, as I mentioned earlier, that we actually do not need to know the median properties. So all the other parameters we still don't know. And let me just give you a brief description. So actually, how can we get this kind of result? So the main tool is very simple. So we have the following 2-parameter meter Leffler function defined as this infinite series, and everyone working on fractional diffusion knows that this function has many fascinating properties, and one of them is that is the following asymptotic decay property. So on a sector contains a negative real axis, so it has the following polynomial decay, linear decay property. So that's one of the important property known from 1960s. So, and using this very simple property, so one can show the following thing. So if we assume that these parameter, unknown parameter, actually they satisfy the condition I mentioned earlier, then so one can show that actually the solution U, so this U given the solution U, so which depends on these parameters. So we do not know a lot, but we know that actually this guy will be analytical function from T1 to infinity if we restrict it. So, and it will take a value in C1 omega. So this means that at least this flux measurement, so we defined it here. So it actually will define a quantity. So that's a first point. So the function, the solution, so even though we do not know the parameter, but we can show that the solution or its normal derivative will be analytic in time for large T. And moreover, so we can show that it's not only analytical. Actually, at large times, it also has the following very simple asymptotic behavior. So it will decay like T2 minus alpha if initial data is non-zero. And if it's 0, so it will decay like T2 power -1 minus alpha up to some constant, which is still unknown. And so that's the second thing. Again, so this result just follows from the property of this Mitter-Leffler function. With these two simple properties, then we can immediately show the main statement. So first is our assumption is that actually so the flux will be equal on a small time interval away from where it vanished. And then, so because we already see that this guy, so they are actually analytic. So this means that in T, so we can extend this guy to up to infinity. And so essentially, so given the measurement, so we have this flux measurement up to infinity because of analyticity. And the second thing is that at a large time T, so we know that the flux will decay like T2 minus alpha K. And if the constant here does not vanish, so clearly, so we can immediately deduce the decay rate immediately. And this is indeed the case. So if we can show that this constant actually will not vanish, and this can be shown that if we apply, for example, maximum principle for elliptic equation and then Hopf lemma, so one can deduce that this guy is actually not vanishing, and under some minor conditions, so I imposed in the theorem. So for example, if the initial condition does not change the sign, or the other terms similar does not change the sign, then we can deduce that this quantity here, so they will not vanish. So and so just by comparing both sides, so we can see immediately that the order of the derivative so can be determined. So without knowing all the quantities. And then numerically, so we can also, based on this kind of observation data, so we can also try to recover the order directly just by looking at the asymptotics. So if we assume that actually we have this measurement for a really large time horizon. For example, here's some numerical results for the subdiffusion case. If we consider the domains 0, 1 and with different initial condition and source term. And you can see that at the large time indeed, so the decay is like, because we plot in a log scale, so it decays like linearly. And based on this linear decay, so you can clearly deduce this fraction order very easily. And we have done some experiment like this. So if we assume that we have measurement on some time interval, then just do a simple least square. So we figure out that we can recover the order relatively accurately if there's no noise in the data. And if there's some very minor noise in the data, so surely accuracy will not be so great, but it's still reasonable. And another thing is that the time interval we take for least square, so clearly it's important. So for example, if you take something very close to T0, then this will not be so great. But if as long as it's sufficiently large, the time horizon is not too small, so we can see that the accuracy will be quite reasonable. And here's some results, the diffusion wave case. So in this case, so we can, so this means just alpha between 1 and 2. And one can observe a very similar asymptotic decay. So at the large time, so we still have a linear decay. So if we look at the log scale, but before we actually kick in the asymptotic regime, so we can see that there's a lot of oscillations, especially if fraction order alpha is large. And this is not very surprising because in that case, so the corresponding function was still the Mitter-Leffler function, but the Mitter-Leffler function will not be completely monotone in that case. And so it So this just reflects that we have a lot of oscillations. But in any case, so we can still see that as long as we can take reasonable large time, so the order alpha so can be indeed estimated from one point of measurements and without knowing anything else, as long as that these other parameters satisfy very mild condition. So that's the first problem. So let me now turn to the second problem. So one natural thing to ask is that so given this piece of information, so actually can we recover a bit more? So instead of only the order, so that's probably not too interesting because it's just a constant, so it's not too exciting. Can we see a bit more about, for example, some of these other parameters in the red? And in general, so this turns out to be quite challenging, and by now it's still quite open. So we have no idea to address this very general case. And so in order to make the problem more manageable, so we will make some simplification. So we will assume that actually our domain is quite simple, so it's just a unit interval. And we will take measurements at the left end point of this interval. And furthermore, so we assume that actually now the boundary condition is known. So we still have the source and alpha and U0, so still unknown. And also the elliptic operator, so I'm trying to be less ambitious. So I only assume that the lower order term is unknown, but the leading term is known. So this guy is known, but the second term Q is unknown. And now, so we just measure this U, so at the left end point. And then we try to recover some of the parameters, so like alpha, Q, and U0 or F. So that's the problem, so which is less ambitious than the previous one, but we try to do a bit more. And for this problem, so recently, so we proved that as long as our boundary conditions, so it satisfies some very mild conditions. So for example, initially it vanishes and then it's non-zero. Then, so we can show that this measurement given this form. So actually, so one can uniquely determine the alpha potential and U0 if we assume F is known. If F is unknown, then so we do not know U0. But the first two parts, so they are known, just from one piece of information. So that's the main results. So let me also briefly give you the flavor. So how can we get this kind of results? So the key step is that actually, so we can represent the solution or the measurements in a very simple form. So again, so the key tool here is we have this meta-Leffler function and this lambda n. So these are just the eigenvalues to the elliptic part. So which is unknown because the Q is unknown. And anyway, so they will exist and we can write them in this form. And so this means that the measurement we have actually consists of two parts. So the first part so comes from the initial condition and the source. And the second part so comes fully from the boundary, can be decomposed into two parts. And let me emphasize that the quantity on the left-hand side is actually known, so on some given time interval. And everything else, like the red stuff, so they are unknown. For example, this low n is unknown because U0 and lambda and this eigenfunction phi n, so they are unknown. So this low n is unknown. Alpha is unknown. And the lambda n is also unknown because this guy depends on the potential. So this is also unknown. And similarly, the second term, so everything in red so is unknown. And this GS is a known quantity. And so clearly, it follows from this representation that we need to analyze these two functions a bit more carefully. So like this infinite summation in color and also the the other infinite summation in color. So we need to analyze these quantities a bit more precisely. And it turns out that both functions, they are actually analytical in T. So the analytic function. And this is true because this meta-Leffler function is the analytic function. And furthermore, so one can show that the Laplace transform of this function actually has a very simple form. So both of them can be represented as infinite series given here, and they have very simple form. And based on this simple facts, so we can now proceed to show you that how can this recovery result I showed you earlier that actually can be true. So this step is actually very simple. So let me just indicate it here. So the first, because we have the G so vanish at the beginning. So this means that our measurement can be represented in this manner. And because we measure this quantity over some interval, and the function involved is the analytic function. So this essentially means that actually we have these two functions equal to each other, and both of them they are analytic. And by the decay property, so this the constant term, so they must be equal to each other. And the remaining term, so because this is now defined over the positive real axis, so we can take a Laplace transform. And according to the previous slides, so they have a very simple form given here. And if we now look at the functions on the left-hand side and the right-hand side, so both are actually holomorphic functions, and they have the corresponding poles. And then you can easily deduce that this alpha and the pole locations like lambda k and rho k, so they all must be equal to each other. And this just gives the first statement. And so what we essentially show here is that because the alpha, rho k, and the lambda k is known, so we have this guy on a small interval there because of analyticity. So we actually have it for the positive real axis. So that's the piece of information that we get. So if we look at the measurement over a small interval. Now let's move to the next subinterval. So over the next subinterval, because the problem is linear, so we already know that our measurement can be decomposed into two parts. So the part in blue is actually already fully determined. And the part in red, so it's we will measure. And then, so what we have is actually the part in red. So we have two of them. They are equal to each other. And then by our assumption, so this function GS actually does not vanish